Hi, good morning, good afternoon, and good evening, everyone, depending on where you join us from today. I'm so happy to welcome all of you today, again with Seth Juarez, who is going to bring us an awesome topic again, so getting started with deep learning. I'm very excited. How are you guys feeling?
I'm excited. I got a lot of stuff. Hopefully we have enough time. I might go super fast, and if I'm going too fast, people tell me to slow down, okay?
Yes, we will let you know. And you guys don't remember that we had a session 2 weeks ago with Seth already that was about getting started with machine learning, which was also really amazing. So if you have missed that, you might want to check that out later on. And with that, I think it's a good time to give you a quick introduction about what is AI42, and then we switch back to you, Seth. Is that all right? Great. See you later. Hi, welcome back everyone to another AI42 session. Håkan, could you tell a bit about what is the motivation of AI42?
Yeah, sure, Eve. So the main idea here is that we would like to give everyone a chance to get into this interesting field of data science and machine learning. So in order to do this, what we've done is we've invited industry experts and recognized speakers. So they will come to our sessions, and we will stream the sessions 2 times a month on Wednesdays at 5 o'clock Central European Time. And the way that we've done this is we've started out with mathematics, with statistics, and with probability theory, and then we've moved into different types of languages like Python and with R and SQL, and then we'll go more into tools like Databricks and Power BI, and you will also learn how can you set up your own machine learning pipeline. And then we'll also go into more advanced topics like reinforcement learning and explainable AI. And in addition to these sessions, we will also have some more practical workshops where you can actually put the theory into practice.
Yes, and you will be able to connect with the best-in-class experts from all around the world, and you will be able to join and collaborate with the community in the field of AI and data science. And for that, you only need to follow us on Instagram, Twitter, and Facebook. And if you would like to watch our previous lectures, you can go to YouTube if you follow the link that you can see on the screen, or you can see our upcoming sessions if you go on the Meetup link.
Yes, and we would also like to take the moment here to thank our sponsors. So we're sponsored by Microsoft and Miles, so thank you so much for sponsoring us.
And we also would like to say a great thank you to our supporters like Global AI Community and C# Corner. And we also thank you a lot for our awesome intro music that you could hear during the stream that is done by Mina Marie. And our amazing graphic designer, Levente Ponger, who made all our graphics for the speaker cards, for the stream, and so on. So thank you, everyone, a lot.
Yep, so should we get back to Seth?
I think it's time to do so. Hi, Seth. Welcome back.
Howdy doodle. Got to get the smoke out of here. There was a lot of smoke everywhere.
Yeah, we really like it. I think it feels like a bit, shady, right? Like
Yeah.
What's going to happen now? Yeah, so what is going to actually happen today?
So today we're going to be talking about deep learning. I am going to review some of this. Well, last time we did a talk about machine learning in general, and I motivated how it works with something called the perceptron. Today we're going to take that a little bit further. So there's going to be a little part review that I'll intersperse, and then I'll show people how to use PyTorch to solve 3 different problems. We might not get to the last problem depending on the time, but for sure we'll get to the first 2.
Yes, and I'm really excited to hear more from you. And before we give you the stage, just a quick practical information that feel free to post your questions in the chat because Seth is going to answer them either during the session or after the session.
Correct.
And I think with that, we bring back a little smoke.
Yes.
So everyone can get ready for what's coming next. And then the stage is yours.
Got to get the smoke out of here. Hello, my friends, and welcome to Getting Started with Deep Learning. My name is Seth Juarez. I work at Microsoft as a developer advocate. Good morning, Gabrielle, Ashish. It's good to see you. I'm looking at the chat. If you have questions, tell me to slow down. Hurry up. Whatever you want, let me know. This is for y'all. So let's start with the agenda. Today, we're going to look at machine learning is a little bit different. I'll go through this part. It's similar to what we did 2 weeks ago, but I'm going to go through it a little bit faster. And then we're going to start talking about how data is the key. We'll talk about tensors, data sets, and data loaders in PyTorch. We'll talk about how to actually craft machine learning models using PyTorch. And then we'll talk about how to make the models better using these concepts called loss or cost, and optimization. And then we'll talk about using a model to save load and use models. Remember, the thing about it is that machine learning is a bit different. Remember, programming is like this. When we have a problem, we think of a series of steps to solve the problem. We give the input to those series of steps, and then out comes an answer. Machine learning is different. Machine learning flips those things around. Instead of actually having an algorithm, what we do is we give the answers and the input to this machine learning process, and out comes an algorithm, or this thing we call a model. These are this is the nomenclature for the things that we had before. We had this, which we understand from programming parlance, but this is what we call it in machine learning. In comes the data, out comes the model, and once you have the model, that's great. The question is, what happens in the box? Last time we actually motivated it from first principles and built the thing. This time we're going to use PyTorch, and once you have that, then it's back to the same thing we had before. In comes the data into the PyTorch, out comes a model/algorithm. We use that model/algorithm with input, some code in there to run the model, and then out comes the answers. It's pretty cool stuff. But the reality is that data is the key, and I am a computer vision person. Oh, I did not do these right. So we're going to do these 3 examples as fast as we can. We did this one a little bit. Let's see if we did this one a little bit 2 weeks ago. We're going to do it again, but in PyTorch, so you can see what it looks like. Last time when we did it, we had to write everything ourselves. You're going to see that PyTorch makes it a little bit easier. Then we're going to go to this one, digits. I'm going to make a model. It's not a perfect model, but you'll see what it's doing. And then I'll just show you an example of this one in a bigger framework. So we're going to do these two. These two we're going to do in PyTorch, right? And then this one I'm going to use something called PyTorch Lightning, just to show you. And my writing is terrible. Terrible. All right, so let's get to it. The question is, anytime we look at these things, this thing, right? This is a function, right? Think about it like there's some function h, and you pass in some variable x, and then out comes the answer, right? This is what this model is. So we're going to call this model h of x. Moving forward, I did this. So this is h of x. So the question might be, well, what does the x look like? So we'll start with the first problem because it's the easiest to visualize. The 9-square problem is basically this one. You have pixels like this one. 1 pixel, another pixel, and they're grayscale. So it's a number between 0 and 255. So this is what the x is going to look like. This is what the y is going to look like, right? So this tells me that it's darker at the top versus darker at the bottom, right? That's a machine learning problem we're trying to solve. Is it darker at the top or darker at the bottom? It's a really dumb problem, but it allows us to actually visualize what's going on. Again, so the problem we're solving, the machine learning problem today, is it darker at the top or darker at the bottom? The x looks like this. This is the input, and this is the answer, y. So let's see how PyTorch deals with these things. So we're going to look at 2 things. Tensors, 3 things: tensors, data sets, and data loaders. So let's go over to my handy dandy here. So this is how we describe things in in PyTorch. Man, I don't know what's going on with me today. So this is PyTorch. Notice that it's connecting to the kernel. By the way, this is Jupyter. This is Azure Notebooks inside Visual Studio Code. So it's loading up this package. Looks like it's using PyTorch 1.8 with a GPU, right? And this is how you define tensors. Or remember, because before when we had this thing, we wanted to figure out how to describe these things and what data structures to store them in. These things are called tensors, and this is how you use them inside of PyTorch. So, for example, I'm making a random integers 3 by 3. Notice that I've basically made random 9 square things, and remember, it's just a square with a pixel here, and that's what these numbers are. Notice I can just make them at will. I can add numbers to them. Do you see that? There's X and Y. And then now I can just add them together. It makes a new one. If I want to add in place, because these tensors are super big, notice that I can add with an underscore. Let's make some more 9. Let's make our 9 squares here. Notice that in this case, I'm making 200. I'm making a huge tensor that has 400 3 by 3 things between 0 and 255. So notice that this tensor basically holds 409 squares. And you can see that once you start to use these data structures, you can basically build a ton of things. Let's go down to the next one. You can actually reshape the way these things look, right? So here's the 9 square, but flattened. There's 400 of them. Then we can do some like multiplication, for example. Here is the X matrix multiply times this thing. But now this what this does is this adds the top, adds the middle, adds the bottom. We did this a little bit last time, you remember, but this is a way to do it in tensors. You can also get the argmax. So for example, this one tells you it's darker at the bottom, darker at the top, bottom, middle, and then you can do a ton of things like multiply things out, and then just to show you that this is a real thing, these 9 squares, the X and the Y's, are basically look like this. And now I think I mistakenly told you top and bottom, but we're building on from the last time. We're doing top, middle, and bottom. So this one tells you it's darkest at the bottom, right? You can see all of that goodness there. So these are tensors. Let's talk about the next thing, which is a data set. This is a cool thing inside of PyTorch that lets you group these things together. So if you're not used to Python, that's okay. Notice that what this is doing a data set of square items. Now, a data set is a class that lets you pull squares out. So for example, this one, there's the class. I'm going to make 256 squares. And notice that for each one, I can print square 34, square 254, and square 25. And notice that not only does each one give you the 9 square flattened, but it also gives you the top, middle, or bottom thing. And you can see that this is actually really cool, because ignoring this thing, this is me forcing the answer because I know the right answers. But basically, it will return the X and the Y, and then the size. And these are the only 2 things that you really need for a PyTorch data set, which is super cool. All a PyTorch data set does is it allows you to aggregate the data and then pull data out one by one, which is super cool. So that's the first thing. So we did that. The data loader is interesting because the data loader allows us to batch things together. So let's go. I want to draw this so you know what I'm talking about. So a tensor is this thing right here. This is a way to hold numbers. Hold numbers, right? It's just a multi-dimensional array, if you think about it. The data set aggregates units of the things we're trying to learn about. For us, it's the squares, right? But notice that it has tensors inside of it. The data loader allows us to batch squares together. So what do I mean by that? So let's just say I want a batch of 10 squares at a time. What this will do is it will use the data set and give you 10 squares at a time and help you load them up. Because sometimes, for example, these squares are ginormous pictures and you have to load them by batches. And so that's what that is doing. So let's go back to this here. You can see here, I can I can get this notion of a square, which is 2 tensors. And then in the data loader, I'm able to get a batch of 5. 1, 2, 3, 4, 5. There's the 5 x's and there's the 5 y's. Okay, so we did that. Fantastic. Tensors, data sets, and data loaders are PyTorch constructions to be able to get the data into a format that then PyTorch can optimize. Awesome. Let me make sure I want to get the questions here. Make sure there's no questions. Oh, okay, good. Everyone's good so far. If you're not good, let me know. Okay, so we did this. You notice that just a little reminder in a different color of what we actually did. We looked at a square data set that held all of the x's and all of the y's. You can see here are, oops, I drew that too fast. Here is the x's. Remember, before we were able to make these things at random there, and then here is the y, and this y basically gives me the answer from here. Okay, fantastic. And then we looked at the data loader. You recall, is this was able to give us batches of 5, right? You can also do some other things with data loaders to make it more efficient to load data. All right. So creating a model. Remember, this is my favorite quote. Machine learning is a lazy way of writing functions, but with data. That was Dr. Internet that said this. Very famous Norwegian professor. So we did the X. We know what that is. What does the H look like? Remember, we want to know top, middle, or bottom. We're going to do top or bottom this time. And just a reminder that we decided on a construct that looked like this, such that if we gave this thing, I think it's 1s here, 0s here, and -1s, this will, if we multiply the X with this number, multiply the X with this number all the way over, we decided that the output is either going to be negative or positive, right? And if it's positive, we guess the top. If it's negative, we guess the bottom. And this actually works, right? So if we multiply, basically we're adding these 3. These ones we're zeroing out. These ones we're adding and then multiplying by a -1. And then this is a +1. And then these sides like fight each other to the death as we add them together. And if the number is positive, we guess top. If the number is negative, we guess bottom. And you notice that that actually corresponds with the actual thing. This bias term, you recall, is, let's just say we want this to be like within 10% of the bottom. What we can do is we can add 10% of the bias on a positive scale, and that will bias it towards answering the top. Fantastic. This thing that we just invented, this W and this B, is the actual model, and these are the predictions. The question then becomes, what about top, middle, or bottom? Or we just make 3 of them, 3 of them, right? And then it starts to look something like this, right? Where the W is not just a set of numbers, like remember before it was 1, 1, 1, 0, 0, 0, -1. Now it's a matrix or tensor of numbers. Now you're starting to see why we do stuff with tensors. And then we take the dot product between this and this. The inner dimensions need to match, you remember, for it to work. And basically a dot product, what it does is if you take, I'm gonna imagine if you're grabbing that long vector and you're turning it on its head, and then you're doing num, num, num for each of the 3. It's like you're doing a dot product with each of the rows of the matrix. And basically, if you think about it, when you multiply these by 1 and add them, you get this. When you multiply these by 1, see, and then add them, you get this, and so on. And now you're just looking at the argmax for the right answer. If it's dark at the top, middle, or bottom, this also becomes a model, like a so. So I went really fast. This is because we kind of went over this last time. I'd love to hear your questions about that if you have any. We've basically constructed a model out of 2 tensors, a W tensor that's a matrix, or a dimension 2 tensor, and then a bias, which is a dimension 1, one-dimensional tensor. These are not scalars. Okay, so how do you build these in PyTorch? how do you actually do that? Remember before, we actually had to have W transpose X plus B. Remember, we actually had to literally write that out. We did like X dot, W plus B. We had to write this in NumPy. How do you do this in PyTorch so that it's a little bit smarter? So let's take a look at that inside of this one. Now you're probably wondering, well, when are we going to get to the deep learning? Well, you got to do with the shallow learning first. So you remember that now we have our square data set, we have our data loader, and yeah. So what we're going to do is we're going to get this going. It's connecting to the kernel. Give it a hot second. All right, so there it is. Now we're literally going to define this model. That's what we're doing. All models in PyTorch inherit from nn.module. You can make as many modules as you want. The cool thing about this is because it's class-based, you can make little complex, little simple mini structures, and then you can aggregate them together in a super module, which is really cool. So there's two things that you have to do that you need to think about. The first is, what are the data structures that we want to have? Remember, we need a W and a B. It turns out that this is such a well-known problem that this is basically called a linear model, right? And so this defines the thing. And here's where our W and B lives. Forward basically says, how do we execute h of x? And you can see here that basically I call the first layer and then I get x out. This is how you do that W transpose x plus b. So let's print out some squares. We made 60,000 squares because we can. Okay, so this is how you do it. I guess we'll get to a little bit more of what this looks like later on, but basically to construct a model, you basically say linear model bracket, and then that's your model. I don't know why I don't just write it. So let's just say model equals linear model. Boop. Oh yeah, I gotta give it an X and a Y. I have those. Wonderful. So let's do this. How do I move this down? No, that's not what I wanted to do. There's a way to move these down, but derf, you just move it down. So notice that now what I can do is I can take square data set. So for example, I can take squares I. So we'll do squares 0, right? And then we'll take the 0th part because that's the X. And then I can do squares 0 and then get the Y. I think this will work. It maybe not. But you'll see in a little bit. I don't want to spend too much time here because I actually run these in a little bit. Right? You can see. Oh my gosh, I'm so dumb. I literally make it right here. Right, there's the linear model. I have to tell it the shape. So it's 9 by 3, right? There is the X. There is the Y. And then notice that here in the model, there it is. You can see the weight and the bias, which is the W and the B. Okay, I spent an extra 5 seconds doing something that's already did because I was smarter than I thought. There you go. So that's what this is doing. Notice that this linear model has inside of it the W here. This is the W. And then it has the B. And then you're probably wondering, well, where is it getting these numbers from? It invents them because we haven't really done anything with them quite yet. All right. There you go. Notice that we instantiated the model. By the way, this was really dumb of me because like all this number is, this says how many, this is our 9 squares. We have, let me delete that because I want to be clear. This linear model says that the size of our X is 9. So it's 9, right? So remember, this is our 9 square. And the size of our answer is 3 for top, middle, and bottom. Okay. So that's what that is. All right. So I saw some questions Oh, good. Very good. Just people hanging out. I love it. I love it. Okay. Back to how we're doing it. Now the next time is, well, how do we make this model better? Because you remember, it just invented the weights and the biases. Well, how do we make the model better? How do we get the W's and B's? And we're going to do this really fast because this is something we went over last time a little bit slower. How do we get these W's and B's in a nice way? Well, what we want to do is we want to minimize the amount of mistakes we make whenever we use the model. And so I'm going to invent. It's really invented by other people. I'm going to show you a formula that I want you to look at and think about. Remember, this is the function that predicts, right? This is the actual answer. For us, right, the x is that thing that's the 9 square, right? That has the 255, 138, right? This is 9 square. The y is a vector of size 3 that has a 1, a 0, 0 for top, 0, 1. The reality is that mathematically, if I make it a -1, it actually all the numbers come out nicer, but I didn't do that, so forgive me for that. So that's what the y looks like. The prediction that it produces, h of x, this whole thing will produce a vector that says there's a number here, I don't know, 300, 5, 2. And so what we have to do is we have to compare them. So from this, we get an argmax that produces a vector that says 1, 0, 0, because that's what our function does. Now, here's the beauty of this. When you subtract two vectors that are exactly the same, right? This minus this will yield a 0. So this function here, right, if it's right and we subtract off the right answer, will always yield a 0. Anytime we get it wrong, it will not be a 0. It will be something greater than 0, right? And then we square it. This is called the sucky function. This says how bad we are at it with our model. And what we want to do is we want to minimize the sucky function. To be clear, remember, this is W transpose X plus B. This is the function that we're making. So how do we minimize the amount of errors that we make such that these parameters minimize this particular function? By the way, for those that are watching, this is the MSE function, or the mean squared error function. So just a little reminder, this kind of looks like, if we jumble this all together, I probably should have used some other value other than x. Let's just use the value d, right? Let's pretend that all of this is just d. D squared looks something like this. Now, if we're a blind 2D Mario and we want to push him down, how do we do that? Well, it turns out that Mario can do something fun, like put his toe behind him and put his toe in front of him, and then look at what this slope is. So, for example, he can go a little bit in the direction of the y. So a little bit in the direction of the y. He can go in a little bit of the direction of the x, and then he can divide them, dy by dx. And then what he can do is he can make these little, I should have said deltas, but these little deltas he can force to go to infinitely small. And then this basically is a derivative, which is calculus, right, for measuring slope at every point along a function that's infinitely, like it, this dy and dx goes to infinity small. So what this does is this tells us what direction we can actually go to, because we want to walk in the direction of the negative derivative is basically what's happening. All right. Making the model better. So to sum up, the model is the function shape we construct. The cost or the loss function is a function that tells us how bad we are at predicting, which is awesome. So the reality is that we want to somehow get the gradient, which is the same thing as the derivative, but in vector space, in tensor space, with respect to the parameters w and b of this function, right? And that tells us how to change the values of W and B in a for loop, basically. The optimizer, what it does is a method for reducing how bad we are at predicting. Now, here's the deal. Calculating gradients of W transpose X plus B is easy. But let's just do a 2-layer neural network, because you're probably starting to realize that this little thing that we build is like the beginning of a neural network. Hopefully you're all like, yeah, that's it. So now if I were to make W transpose times, let's just say W Z transpose X plus some bias C plus B. Now, oh well, this isn't even the neural network. So let me draw the math out completely so you can see, and then I'll show you why this is this way in another second. So we have W transpose times some function, right? Times some function, and then we'll do I don't know, Z transpose X plus C plus B. This is now a neural network, a 2-layer neural network that uses this same thing. And if it's confusing, I'll get to it in a second, and we'll motivate this again. Taking the gradient of this is much harder. And now think of arbitrarily long structures. How do we take gradients of arbitrarily long structures? Well, it turns out PyTorch tensors are soups special. Special how? I'll show you. Okay, so there is our thing. Here is our tensors, right? I'm dividing them by 255, just to get a scale between 0 and 1. Now what we're going to do is we're going to do our W. We're going to do this all by hand. So there's our W, there's our B. Notice that we're doing our H function. You can see it right here. X matrix multiply W. This is the same thing as W transpose X. Plus B, the loss function is W transpose X plus B minus Y, quantity squared, mean. Not like angry, but like, 1 over N kind of thing. Let me show you something crazy about PyTorch tensors. PyTorch tensors inherently know how they are generated. How, say you? I'll show you. So I'm taking this loss function, which has a tensor, and tensors inside of them. Here, let me show you. H. Inside of them know the function that generated them. They know the function that generated them. Sorry, I have to quit Teams or you're going to hear bling, bling, bling. And that's the cool thing about it, right? That these tensors know what generated them. So this grad function tells it the thing that generated, and I can actually build a tree, right? This is not me like saying, this is me. I'll show you. Let me add 50 here. I don't need to do that, but okay, look at this tree all of a sudden. You see this? Now it's different because it knows, like, these are constants, right? These are the actual variables that we're interested in. This is W and B because those are the ones that we are interested in. These are constants. And why you're saying, well, why is the X a constant? Because it is. It's this constant. And you can see that this knows about the structure of the tensors, which is awesome. Because the thing about derivatives, and you all might know this, is that derivatives of a complex function. So let's just say, let's say a gradient with respect to some parameters p of a complex function f of g of x, right, is the derivative of the outer one. So f of g of x times the derivative of what's on the inside. Now, if your function is like f of g of h of x, right, which is what these functions start to become, then this becomes the derivative of the outside, f of g of h of x, right, times the derivative of what's on the inside, g prime of h of x, times the derivative of the one that's on the inside of that. Notice that all of a sudden, the gradients of these things are chained based upon the operations. And that's why PyTorch is so fantastic, because it remembers how those things were generated. So you can literally say loss backwards, and then you can get the gradients with respect to these variables. Boom! Huh? That's why PyTorch is so cool. You know what I'm saying? Because it actually understands not just the functions that generate, not just the tensors, but it understands inherently the gradients with respect to. So this makes it so that these you can create what are called dynamic function graphs that can change with if statements and still maintain how these tensors were generated to create, their gradients. All right, let's see. Questions here. It says, I thought we will, this is a sheesh. It says, I thought we will get model from data, but we already have the model here. If I'm understanding fine. Great question, Ashish. It turns out that the dirty secret is you have to pick a model shape and then see if that model shape performs well with your data. There is no, you have to pick the shape. There's no magic there. It's like saying, let me try this one. And then if it works, it's great. If it doesn't work, then it's not great. You try a different model shape. In scikit-learn, for example, there's model shapes like logistic regression, decision trees, SVMs. Those are like stamped out shapes that you either use or you don't. For deep learning or for neural networks or these kinds of models, you can actually construct them, which is what we're doing. Okay, fantastic. Now let's take a look at our linear model here. You remember we built this linear model. We'll shift enter here. Now just to show you this W transpose, this H, sum, H of X minus Y quantity squared 1 over N is so common, it's mean squared error, that you can see that it's already built into PyTorch. So now notice that to run the model, right, I give it an X, I calculate the cost, and notice that I can draw this function, right? In PyTorch, you can see that there's something called the mean squared error, right? You can see that there is this thing called this. I added a softmax, a const, add matrix multiply. All of that is in there, right? And it's built up. So anytime I want to construct a gradient of this linear model, it's built in. It's bananas, BANANAS. Tensors are special. It's true. Notice we have that here. I showed you that one. I also remember I actually also changed this part right here, and then this thing like got bigger because I mean that's how math works. It's fantastic. All right, so let's put it all together now. Let's do the loop here. I think let me put this down. I think I have that one. Where do I have that one? The loop. No, where did I put the loop? Okay. I think it's simple. No, this is the one we did last time. Squares. Yes, here it is. We did this. I don't think we need this one. I can take this out. So now there is the why is this not happy? And then it is defined. Stop it. You can see that I'm doing a cost function. Let's draw the thing out. This is a little bit better, right? Because this is the straight MSE loss, the cost of the model, which is the linear model. You can see that they were super clever because a W transpose X plus B happens so often, they made it into one single operation. So this is the constant. This is X. Sorry, this is B. This is the constant X, and this is W transpose X times yeah, and then the mean squared error. Where is this constant coming from? That I'm not sure about. Okay, so let's get into the actual loop. Hopefully, I don't know why it doesn't. It thinks it's not defined. Just in case, I'll redefine it. All right. So here we go. What we have is we're picking the device. If it's CUDA, that's great. This is a linear model. We're moving the model to the right device. We're using the cost function. And then here is the optimization method. Remember that graph thing that we drew where we step Mario down? This is called gradient descent. Stochastic gradient descent adds batching, which is what the data loader does. And that's why we have it. And so there it is. We did that. And now all we do is we go through the loop. Boop, 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 right? We get the X and the Y. We zero out the gradients. We predict the model. We get the loss. We do a backward. We do a step. And notice, boop, this should be going down. You can see that it's going down soups slow. And now we print out the model parameters, which is the W and the B. And you're like, what? Remember, before we got ones and minus ones. Let me do this. Let me be clever and let me force the issue. Let me go to the square data set, util.square. Let me force the issue here. Self.index times 2 minus 1. Boop. Okay, let's go back to the squares. Let's clear output to restart. Okay, let's do this again. Everyone's like, what the heck are you doing? Question from Ashish, what is the CUDA device? The CUDA device is a GPU. And the reason why we like using GPUs is because matrix multiplications in GPUs are what make it happy. So let's do this. Okay, there we go. That's what it is. The CUDA device says use the GPU. All right, so notice this loss function should be going to 0. That's the goal. Notice it's getting smaller, but not by much, unfortunately. I guess it can't go any smaller. Notice that it gets optimized pretty quickly. Loss, by the way, is our sucky function. We want that thing to go to 0. Wonderful. How many epochs did I tell it to do it? 20. Okay, so by the way, this is the loop. It's going through the batch. The batch gets, I don't know, how many squares are we getting at a time? I don't know where the batch is. Oh, we're getting 128, 9 squares at a time. And we're zeroing the grad, predicting, seeing how bad we are at it with respect to the actual answer. We're doing backward. And the optimizer knows about the model parameters. And then it subtracts the gradients off. All right, looks like we're done. And now let's go to this. What? Now you're seeing these are close to what we thought. The ones, the zeros, right? And then the zeros, the ones, right? And so notice that it basically has reverse engineered the right answers. This tensor bias is not really needed, so these numbers are going to be mostly the same. Okay. That's cool, right? So basically in PyTorch, we've re-engineered the thing we've done before, but notice that this loop is much tighter, much tighter. We don't have to calculate by hand what the function is for the gradient. It just knows because of the magic tensors. We don't have to keep track of the W's and the B's because those are tracked inside of the model, right? And it's just a really nice way of abstracting things. Okay, so let me go back here. We did the loop. Thank goodness. We did this gloriousness. It was fantastic. We also, I went in there and rehacked it a little bit because I wanted to show that it got ones and zeros-ish. But it's pretty cool. All right, so let's use the model here. Now that we have our model, let's just use it. So here's how you do it. I'm making a new image, right? Here are the labels, top, middle, or bottom. Notice that Torch NoGrad says don't keep track of the gradients, so it doesn't, right? Now there's O. Let's print O out. There it is. Top, middle, bottom, and then the answer is bottom for this one, right? Because this is the this is the argmax. I wonder why their numbers are so negative. It doesn't matter because basically it's the bottom, and you can see that that is actually the case. So let's do this. Let's try it again. If it doesn't work, this is making me nervous. I wonder why it's not doing the right thing. So 255 should be dark at the top. And indeed it is. Right? Can you see that? Now let's do 120. Let's do 12s here. And then let's 255s the middle. This is how we use the model. And that's it. I mean, there you go. Okay. Life is good. So this is cool, right? I mean, we basically figured out how to use the model, and that's basically it, right? Just quick review. Machine learning is different. Data is the key. Tensors, data sets, and data loaders. We crafted a model. We did a loss cost optimization, save, load, and use. Digits, though, we promised to do some digits. Well, notice that now it's just like this, and the vectors are just much bigger, right? And so instead of this, we have something that's like this. It's bigger. Top, middle, bottom. Remember how we had 3 of them? Now, if you think about it, it's like doing this, right? Top, middle, bottom, except there's only 3 of these. For digits, we're going to need 10 of these. But what if we stacked them? What if we added another layer and then we stacked them again? Remember how we were doing that before? We had like a W transpose times a Z transpose. I'll do this wrong so you can see it. X plus C plus B. That's what this kind of thing is doing. But the thing about this is that a linear combination, this isn't a neural network yet. The linear combination of a linear combination is still a linear combination. So you get no extra power. So what they do is they add functions in between. These are called activation functions. Activation functions. By the way, I'm motivating neural networks now. So now we have W transpose times some kind of activation function, Z transpose X plus bias in there plus B, right? This is a 2-layer neural network with an activation function. You can see right there. And so now these things start to go like this, right? This is what we're going to actually build. We have the numbers coming in, and the numbers are I think it's 28 by 28 pixels, and then so it's 784. We go through this, we do an activation function, we do it again, activation function, and notice that as we go over the matrices are getting smaller. And then here's another activation function. This activation function is nice because it forces all these to sum to 1, which makes it look like a probability, but it's not. What does that look like in PyTorch? It looks like this. Remember how we built the thing before? We had a linear layer. So now we have 3 linear layers. But this time when we do the forward, right, we use the activation function here. And then we output the softmax over the first dimension. What? Let's go back to this other goodness so you can see it. Oh, ¿dónde estamos? Neural network, here it is. Sorry, my kids are vacuuming. Here's what this looks like. Boop. Mean squared error loss on this one. Yeah. Notice that we don't have to keep track of the gradients for this one because it does it for us. There's an add matrix multiply, add matrix multiply, add matrix multiply, softmax, MSE, boom. Mean squared error has the 1 over n const. That's the thing I'm trying to remember. That's the thing I'm remembering now. There you go. There's the activation function. I'm sorry. There's the whole model function with the loss in there. Isn't that glorious? So let's talk about, though, why this is kind of a dumb idea for pictures. So notice that the way we're doing it with the linear model is we're taking all these pixels and we're stacking them side by side, right? Because it's one long vector. That's what our linear model does. But the reality is that we're losing this spatial spatial locality across the y direction. So there's some cleverness afoot. There's some things called filters and pooling. So take a look at this. This is a filter. So we're going to divide this up into this square. What we're going to do is we're going to multiply all these numbers together and all these numbers together, and then we're going to put it in here. Then we're going to do the same thing again, right? And then we're going to put it in here. And then we're going to do it again and put it in here. And what the heck does that do other than make the image smaller? I don't know. But let's make it so that it keeps the image the same size. So we pad this. And now when we do this, boop, boop, right, with this, the image is the same size with padding. Now, what if we want to do another operation called pooling? You're probably looking at me thinking, what is he talking about? What this does is this sums these all, or gets the max or the average or whatever, and it puts it into here. Here's the next one. Put it into here. This is called pooling. Now, you're probably thinking, what the heck does that do to a picture? Well, thankfully, I've actually set it up so I can show you. So this just does open and resize an image. That's all it does. This is a filter, a convolution. It's also called a convolution. It's a 2D convolution. I just wrote out that operation that I showed you, which is quite cool, right? The operation that I showed you before, where it goes and does that thing, right? And then I implemented pooling. I wrote it out by hand because, I've got all sorts of time. And then remember, this is the filter we're going to use. 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Hold on. Let me. 1 second. All right. Minus 1, minus 1, minus 1. And notice basically I made this new W. Okay. All right. So what I'm going to do is I'm going to open an image here. It's an important image of the wedding, obviously. And I'm going to run. Let me just show the image, obviously, because it's an important image. Hold on 1 second. Sorry, I'm trying to get my kid to stop vacuuming. All right. Told her to stop. She's still vacuuming. She's not listening to me. So here's a picture of the wedding. Obviously, soup's important. And what I'm going to do is I'm going to take this image and do a convolution over it, 2D, and then show you what it does. Notice that little operation basically found all the edges. Let me show you what a pooling does. It enhances them. Yes. Crazy. Let's do another one. Let's do one of the kids, because the kids are soup's important. Does the same thing. Now let me show you one that's actually really quite good. A fence. Notice that it's finding all of the edges. So basically, these convolution operators and these pooling operators, when you think about it, what they're doing is they're basically generating new images that it can use to learn from. We're going to do this twice and then pass it into this regular linear thing. And this is what it starts to look like. So if we go back to the graph here, here's a convolutional neural network for the MNIST data. Look at this. That's cool, right? So cool. Wait, is this? Yeah, this is. Did I do the CNN? Yeah, CNN, convolutional neural network. You see what makes so cool. You see MKLDNN? It's basically now a different kind of operation, but everything else still works. It's fantastic. All right, so let's do a full run here, and let's do the digits. Let's see if I have it open. Very good. Notice that this is all here. Let me do a thing here because I made these graphs look really nice. How did I make these graphs look so nice? Oh, I know where it is. It's in the kernels. Sorry. I have too many things open. Save. So let's go to kernels here. And let me take this because I made a cool style so that it would look nice. And you can see we can run through the whole convolutional neural network. I'm kind of running out of time. I feel bad. So basically, this draws all the digits. You can see all of them in here. You can see the same thing we did before. The loss function I'm using is different. I'm using binary cross entropy instead of mean squared error because it's a little bit better. And then you can see it's the same exact thing we had before. Digits. And then it just runs through all of it here. And then does it work? Let's try it. I actually put this model inside of a website, Yarn Dev. Here we go. By the way, let's get some questions as it's going here because I want to make sure. Good. Everything's good so far. So let's go into this. So nice. Let's go over here. And let me draw a pic. Let me draw a digit. We'll draw the digit 3. What? By the way, here's down here sneakily. You see this? This is a debug to see what it actually looks like. Clear. Let's do, I don't know, 0. But it's not very good because I didn't train it very long. So watch, I'll draw a 7 and it'll think it's a 2. Or let me draw a 9, right? It thinks it's a 7. And so that's the reality with these models, right? That you gotta work on them. By the way, if you're interested in what this looks like or how I did it, if I go to github.com, I think it's Onyx Web. You can totally look at the sample. It's all there. So there's the index page, and then the components. I have the draw thing. You can see it's all there. You can take a look at it. Okay. All right. So we did machine learning is different. Data is the key. Tensors, data sets, data loaders, models, blah, blah, blah. Now let's do this final one that I promised that I would show you, but I'll show it to you in PyTorch Lightning in the final 2 minutes. PyTorch Lightning makes things a little bit more, how shall I say, did I do this right? I wonder why this is, hold on. Let me open this correctly. So Rochambeau, there you go. That's how I wanted to open it as a workspace. Okay, so here's the AI for Rochambeau. Notice that PyTorch Lightning puts everything into a special place. So we have the model. There is the model. Oh wow, this isn't even using a convolutional neural network, but that's fine. So here is the model. Oh no, this one I see what it's using. It's using a transfer learning. Here's the forward, and here's the compute, and then here's a training step, validation step, and a way to configure the optimizers. This is how we get the data. By the way, the data are pictures of me doing either nothing, paper, rock, or scissors, right? And basically, when you run it, I have too many things open. You go to this trainer and you run it. So let me show you what that looks like. I can basically, do all of this stuff. So notice it's in the right thing. And I think I just have to hit F5 to run this, or I can just say, yeah, I think it's just F5 to run it. Let's try it. Oh yeah, I just changed something on here. I'm sorry about that. Now I can do it. There it is. It's running. And basically this thing will just train it, and it will learn a difference between me doing rock, paper, and scissors. All right, so my time is up. I'll let it run. Any questions? Eve. As we go through, and apologies, this I'll get this is, you can totally look this up, by the way. It's on I do it on my AI show every other week. And so AI Advocates, Rochambeau, you can find all the code in there. I recently made a change that broke it, and I'd have to go in there and fix it, and I just don't have time to do that. But basically, it's really easy to run. I didn't put in the reading, but it's basically Python trainer.py // All right, thank you for that. I am out of time, but let me answer one question. Apart from image classification, how is PyTorch being used in applications? What can be found in real business scenarios? PyTorch can do anything from text, language, speech. It's just a question of creating the model and putting the input data into Tensors. Great question. All right, I cede my time back to you, Eva.
Wow, Seth, thank you. That was really exciting again. I really found it really, I mean, it was awesome. I don't even find words.
I wish I had more time to go over the other one. It's just I want people to understand PyTorch and deep learning. It's pretty cool stuff.
Yes, and I think they got a really good start to get into it. If you would be so nice to share some links with us, there they can go and look for more information. That would be nice.
Oh yeah, absolutely. The all those notebooks I showed you are all on GitHub. Just Seth Juarez, github.com/Juarez, deep learning with PyTorch, and even the slides. Except I changed them so they match what I said. Deep learning with PyTorch. Yeah, it's all there. I'll commit the changes that I've made recently, so you can all go and look at those notebooks that I showed you. It's all in even the slides are there too.
Thank you a lot. That's really cool. And while we're waiting for more questions, I want to say a great thank you for your session, Seth. It was really exciting. And we would like you guys, the audience, to give us your feedback about what you think about the sessions of AI42, which for that survey, we will share the link in the chat. And if you have further questions and while you're watching the recording, you're welcome to reach out to us on Twitter or Facebook to AI42, and you can find us and we'll get you the answers.
That's right. And sorry if you heard a vacuum cleaner. I told them to stop vacuuming.
We actually couldn't hear it, so it was
good.
fine.
Oh, good. It's my microphone. It's real good. It's directional. So.
And,
yes,
yeah, and Eve, isn't there some more interesting stuff going on tonight?
That's right. Don't forget about the thing.
Oh yeah, let's not forget about that. Yes, some exciting stuff comes up tonight in our time in Oslo time zone at 7 p.m. We're gonna get started with our area at Global AI on virtual tour. So Global AI community is going to come to Oslo tonight, and I'm going to be the host there, where I bring 4 amazing speakers talking about some great solutions in the field of AI. You can join us with the link that we're also going to share in the chat. And I think with that, we say a big thank you for everyone for joining us. I think it was really amazing today as well. So thank you, Seth, for talking about these amazing topics. And I hope we will see you back at some point.
Mm-hmm.
I hope so too. Thanks for having me.
Yeah, and actually, we will see you back quite soon, actually, because in 2 weeks' time, on June 30, we will have a panel discussion where the topic for this is how you can turn your passion in AI into your career.
Oh,
so
that's right.
Seth will be one of our panel participants, and we also have JP Vogt, and Wei Meng Lee, and Heine Ilmarinen. So we welcome all of you.
Yes, we basically bring back all our experts of AI42, and we will talk about how can you also be an expert in the field. That will be cool.
Awesome. Well, I'm excited to be here. Thanks for inviting me. And if anyone has any questions, feel free to reach out to me on social media or Seth.Juarez at Microsoft.com. Happy to help out.
Thank you a lot.
Yeah. Thanks so much.
Take care, everyone.